My name is Volker Lendecke. I work for SerNet in Germany. I've been a long-term member of the Samba team. And I was recently asked by a customer to explore ways to get some common infrastructure in place for both SMB and NFS. And me being a long-term SMB developer, I looked at the various NFS RFCs and I made a talk out of this, of my view of how I see NFS. I have to say that I haven't done an NFS implementation myself, so probably there's a few people in this room who know a lot more about NFS than I do, and please heckle and throw things at me if I just tell bullshit here. But this is my view of spending some significant amount of time in the NFS RFCs with the goal to see where could we benefit from common infrastructure, where do we differ, and how do we cooperate. So from 10 miles above, what are these protocols? What are these things? Essentially, they provide both local and remote access paths to file systems. And this slide focuses on POSIX, NFS, and SMB. And they all give access to directories and files with all bells and whistles, with all metadata and directories, listing, whatever, ACLs, and all that stuff. All three of them come from different historic backgrounds. All three of them carry a lot of history. You could essentially see the POSIX API also as some kind of protocol with some unique properties. So you could see the server of the POSIX API. The kernel could serve as the server of this API. And the advantage that this local API or protocol or whatever you call it has is that you have complete coherence when either end dies. So the client is the application, the kernel is the server, and if either end dies, the other end will notice. If the kernel dies, I mean, the client is dead as well. If the client dies, the server, the kernel is informed immediately and can clean up behind that that process that has died. There is some latency. I mean, every syscall has a latency, but it's very, very, very slow. Both NFS and POSIX are a much more difficult place because first you have latency. You have much more limited bandwidth compared to a local syscall interface. And everything between those, client and server, could lie to you, could drop packets, could duplicate packets, could do everything bad that you could imagine. You might not even notice for hours that the other end has died. You have to take care of cleaning up on either end and so on. I come from the Samba world, and Samba's main selling point is converting a POSIX file system into SMB semantics. SMB semantics is pretty close to Windows. And so they have subtly different aspects, subtly different semantics in many, many aspects. So if you look at what NFS does, it comes essentially from a POSIX world. It doesn't really fully do POSIX because it can't. I mean, deleting files is one thing that NFS can't really do well. SMB comes from the Windows world, so the SMB semantic matches NTFS historically, and it has evolved into, also ReFS and other stuff. S3 is a pretty new player here that is really kind of outside of the scope of this. But as S3 is a very popular access path to files, what they call objects, they also have to be taken into account in this presentation here somewhat. You have to store these files somewhere. And Samba does it on a file system, on a local file system. And if you have different access paths to that same file system, you have to somehow coordinate. And if you look at the different implementations, so we have NFS servers, we have SMB servers, we have S3 servers, of course we have a ton of POSIX file systems. Each of them serves their own niche pretty well. We have a ton of proprietary SMB servers and so on. They all do SMB pretty well. None of them, to my knowledge, really covers the cross-protocol case very well, at least not in the open source world. And I have been doing Samba programming in clustered environments for ages, for customers, for big customers, who actually have this cross-protocol case, who store Samba files on a disk that is also being exported at the same time by NFS. And I've really tried to put focus on getting this interoperability somewhat right. Nobody cares. Why is this so hard? POSIX alone is quite subtle. For example, you want to store a file on a disk. That is surprisingly hard to make sure that to nail down the moment in time when you can be actually sure that a file is on disk. A new file, you have to fsync the file. Then you also, if you have created it freshly, you also have to sync the directory and so on. There's subtleties to this. Also POSIX, you can delete a file, but while it's still open by some handle, I mean, it's still there. That's one of the other subtleties that NFS version 3 can't really cover. But the basic semantics, everybody knows them. There's so much documentation on how POSIX file system API works. The other protocols that we talk about here, SMB and NFS, I mean, they have decades of history. They started in the 80s, I believe, both of them. And yeah, they have expanded into more and more spaces. And with this history, a lot of subtleties also developed in either of those. And if you really want to make the cooperation between those protocols working well, you need to know both protocols really working really well. Otherwise, you really can only ask the other developer on the other side, hey, how is locking in this particular aspect working? This is part of the problem, that these protocols are so complex that you can't be really good at both implementations, at both sides in one person. So we need to develop some whatever community or some forum to really make this work. Why has this never been solved? From my perspective, as I said, I've really tried to convince my customers, give me some budget and let me talk to your NFS developers. We want to just define the failure cases. For example, an SMB client opens a file with share mode nothing, so no share at all. What would the error message given to an NFS client be? Is it text busy or something? I mean, nobody has thought these through, what should happen in these cases. And even getting a common test suite just to define test cases, just to define the protocol semantics between those elements, hasn't done this so far. For Windows alone, Windows clients really expect good, faithful semantics. I mean, that's kind of a joke, I would guess, but it's the CEO's laptop that must work even if the files reside on an SMB server. So SMB is, if there's one thing that Microsoft historically was very good at, that's compatibility to ancient applications. And so everything that works locally on NTFS must also work the same way, maybe a bit slower, across SMB. And they better make sure that this is maintained forever. So this is why SMB is pretty coherent with local NTFS semantics. Right now I work with a development environment where everybody has their home directory on NFS. And So I have to live with this git tree on NFS and C files on NFS and makefile. And every now and then somebody in a Slack chat just complains, hey, it doesn't work, let me reboot the workstation. Oh, let's try NFSv4.1, that might help, and so on. So what I'm saying is, in the NFS world, this coherence, this fidelity to local semantics, in my perspective, is not seen as so important, because these Unix geeks, they are used to whatever. NFS sucks, NFS doesn't really give you local semantics, and they can live with this. So probably just in the NFS world, nobody really cared enough to make a business case out of this, to get this locking, to get the local semantics really right. So where do we differ? And I will cover these topics in more slides in the future. First is security. NFS, either no security at all or machine-based. SMB is always per user, although a machine can also qualify as a user. Then we have ACLs, and I just learned in Charles Lever's call that NFS just reinvents POSIX ACLs. NFSv4 just reinvents POSIX ACLs, having NFSv4 ACLs, which are much richer than POSIX ACLs, but yeah, you couldn't get them through the Linux kernel. So we have differences in file semantics, file name semantics. This is a minor topic, I would say. This is pretty much solved. I mean, you have case insensitivity. Some Windows protocol, you can't have a colon in a file name. You can't have a quote in a file name. This is not really interesting. I mean, you have to take care of it by special quoting or something, but it's not really common infrastructure. Then we have a bit different file and directory metadata, but this is also not really so different. The really interesting pieces to me was, how do we deal with failed clients or failed networks? How do we deal with locking, with request replay, and with how do we deal with client caching? Okay, let's start with security. The SMB protocol, and I really went back very far with a file called core.ps or core.txt describing the initial protocol that I could find. You had password protected shares from day one of the documentation that I could find in SMB. It was a per share password, and very early on they figured out that, okay, per share passwords are not good. We need to distinguish users. I haven't looked at the date when this LANman 1 protocol was initially published, but it's really long ago. I think it's early 90s or something, I don't know. The scope of the security context. So you log into an SMB server. The scope of the security context that you establish with logging in has been the transport connection. With SMB2, later SMB2 releases, this has been lifted to the so-called session that can go beyond a single transport connection. But typically, it's an association to a server, and it has been a transport connection, a single TCP connection. That is the scope of the validity of my login session. NFS instead, on the other hand, relies on the underlying ONC RPC for security. And if you read the RFCs, it's really a per request thing. So every single request carries a full authentication context somehow. And so every request can carry a different user identity, group identity, or whatever. It's not really, the scope is not really the transport connection. The scope is really focused on the individual request, which is kind of strange. So every single request could come in with a completely different security token. And then NFS also, and I didn't really fully understand this, allows different RPC security contexts per directory, or RPC security requirements per subdirectory. So they can say, okay, you can cd into this directory, but you can only do this if you do whatever this level of GSS API authentication. And yeah, that's kind of weird. I can understand where it comes from, because you cross Mount Pines and you want to apply different policies and subdirectories. This is something that SMB does not have. This concept does not exist in SMB, that you can just apply different security requirements to different subdirectories. Then NFS also protects. NFS comes from a world where typically there was no security whatsoever on the wire. No network encryption, no signing, no sealing, no nothing. And they relatively early probably figured out that, okay, we need to do something about locking. Somebody can trip on somebody else's open, locking, lease state, whatever. So they added a special protocol element, assuming that all the transport, all the outer NFS requests are completely unprotected, but we need to protect this particular piece of the protocol, which is open delegations, locking, and so on. And this is a completely separate mechanism somewhere hidden deep inside the NFSv4 spec, yeah, which is kind of mandatory, but which can live outside, which must live on a completely unprotected network. A lot of NFS deployments actually run completely without security. I mean, this is this old joke, NFS means no file security, and still many deployments are non-Kerberized, and people are maybe not happy, but they are not unhappy enough to do something about this. ACLs. Difficult topic. So what is SMB ACLs? It's essentially defined by the Windows security model. It's all defined in a document called ms-datatype dtyp. And the principles that you can assign rights or permissions to are security identifiers. Essentially, in practice, 128-bit UIDs on GIDs. In reality, they are a lot more flexible, but typical deployments just have it as 128-bit UIDs, GIDs. SIDs don't have a type. So Unix numbers don't have a type either, but if you do a chmod, if you do a chown, you assign type 1000, you assign type or gender or whatever type user to this number 1000. At the moment where you say, okay, I chown 1000 on a file, this number 1000 becomes a UID. This concept doesn't exist in Windows. So you can assign a SID to the owner field, and you don't care about the type. You don't even look at that. You can assign group SIDs as the owner. You can assign group SIDs as ACL entries. You can assign user SIDs as ACL entries, and so on. They don't have a type. You have to ask somebody, typically a domain controller, what is this SID? Is it a user? Is it a group? If you care. NFS, SMB ACLs deal with 13 different bits on different aspects of what you can do with the file, like read attributes, like read, write, append, and so on. Look these up. NFSv4 deals with just the 9 permission bits that came from the POSIX specification. NFSv4, and this I can only speculate what they did. My guess would be that they just read the Microsoft documentation about what a security identifier and what a ACL is, and they just coded this into an NFS RFC language. Steve has a question. Jeremy is not here. I don't really have to repeat the question. It's more like a comment confirming that it is really unclear where this NFSv4 ACL came from. And yeah, so my guess would have been they looked at Microsoft documentation at times when Microsoft documentation was not 100% accurate. Pardon? Yeah, whatever. So NFSv4 has 13 bits from the Windows specification. And one thing that you see in NFSv4, if you run on a file system that really exposes NFS or really uses NFSv4 ACLs, and I work with GPFS, this breaks kind of POSIX assumptions. For example, what you can do is you can take away the permission to read attributes from a file. What does it mean? You can't stat a file anymore. In normal POSIX environments, all you need to stat a file is the X bit on the containing directory. And ls-l is horrendously confused if it can see a file name, but it can't stat it for permission reasons. So this is kind of one of the areas where even in the pure Unix world, which I count NFS into, there is, in the ACL space, there is some kind of confusion. So they took these 13 bits, they added 2 more. NFSv4.1 added some more aspects of the Windows ACL model. Deny ACEs, and this is the most contentious aspect of the NFSv4 ACL model that, in my perception, prevents NFSv4 ACLs to be accepted in the Linux kernel. They are supported. There's one problem with this, with the whole NFSv4 thing. You have 13 bits in your ACL, or 15 even, but all the access controls, all the calls where you ask for access, like open, like the access RPC call, you cannot query all of these bits. So kind of what's the point of adding these 13 bits or 15 bits when you can't really query them? In this current login session, could I read an attribute? This is kind of missing for me. There was a question.
Two comments. With SMB, other than the ACL, you also have special attributes like the read-only attribute, which you don't have equivalent in NFS. And regarding the actual access check, with POSIX ACL, you go over the ACL until you find a match for the principal, and then you stop, even if you deny permission. Unlike SMB, where you aggregate.
There were 2 comments. One is we still have the system hidden read-only archive bits that are not covered in NFS. So these come from the SMB world. The other comment was that the semantics of the ACL differ. The semantics of how you evaluate, how you match your ACL against your current login session, against your current login token, they subtly differ. This also needs to be taken into account, of course. So NFSv4 set and get ACL calls transmit strings, full strings, and I have seen both names, but I have also seen numeric UIDs just transmitted as 1000 in ASCII. That's probably the convention from Unix to Unix. User at domain is recommended. Numeric strings are real. I haven't really found a mandatory standard of all of this. Shown in chmod. So if you look at POSIX, the stat information has permissions, owner and owning group. And an important aspect of this slide is these are independent entities. Which means that if you do shown, this is not really well representable in a Windows ACL, and I will explain why. NFSv3 and v4 pretty much implement this model that you have permission bits or extensions of permission bits, and you have an implicit owner permission. NFSv4 says, okay, I have separate entities, separate entries that are named, remember we have strings, that are named owner at, group at, and everyone at, which represent the user group and others. Everyone is a bit blurry here, but owner at and group at represent the user and the owner and owning groups, permissions in the RWX, and so on. And if you look at RFC 18881, there's a whole section about what happens if you do just a chmod. If you do a chmod together with a set ACL, if you do just a set ACL, how the other side of permission bits and ACL are affected. So this is really difficult, apparently. The point is, what do you do when you chmod? Or what happens if you do a chmod? Then the permissions, or the principle, or the permissions that owner at is permitted to do, change. If you do chown, somebody else gets the implicit owner at permissions. And the problem is, this concept of implicit permissions for whoever is the current owner, this thing doesn't exist in Windows. So there is no ACE, ACL control entry, that would give permission to whoever the current owner is. Windows doesn't have this. And this creates all sorts of complications. And as part of our effort to do SMB3 Unix extensions, we have to cover this. What happens with permissions or ACLs or whatever when you do a chown? And this section 6.4 in NFS covers it to some extent, but we have to refine this. But what model do we want? So file and directory metadata. I don't really see much significant difference that would matter. If you ask, yeah, question?
I think it's worth calling out that other users and everyone in the renewable chmod is radically different, right?
Yeah.
Because people assume that everyone and other are the same, but they are completely different.
The comment was that there is that everyone and the others in the POSIX permission bits are completely different things, and this also touches the topic what I said, that the ACL semantics, how you evaluate an ACL, the details, the fine details of that plays into this different aspect. With file and directory metadata, I don't really see much difference. SMB, for example, you can ask with different info levels about a stat, fstat. So I want this and this and this info level, which means I get all timestamps, I get the size of extended attributes, I get the number of streams or whatever. So, and this is combined into like in the order of 10 different active info levels. I haven't counted, but it's a handful plus. NFS has a slightly different approach. They put everything into named or numbered attributes. So you can query attributes by name, which is, of course, a lot more flexible than the SMB approach. It's getting a new info level is next to impossible. We got our new info level for the SMB3 POSIX extensions, but we are discussing to change this. It's much harder than just adding a fresh attribute to the NFS RFCs. Both protocols have named extended attributes, and but these are different from streams. So a named extended attribute is what you would do in with the local file system with the setx, attr, getx, attr, listx, attr, sys calls. They are all very size restricted. Like you can have at most like 64K overall, something like that. But both protocols implement these attributes. Named streams are something completely different. Named streams are essentially more than one file under a single file name. Apple uses these for metadata. Virus writers use this to hide payload in there. So it's named streams are essentially you can open one main file with a normal open calls and with some special naming convention, the colon character or with special NFS calls, you have completely fresh, unlimited size data buckets inside one single file. Bradley? Correction was that Apple uses name streams for extend attributes, not general metadata. Okay. The surprise for me was that NFSv4 defines name streams. I wasn't aware of that. Request replay. This is kind of my observation from reading the NFS RFCs. It's not really relevant for interoperability questions, but this is not how this talk was developed. So SMB was from day one ran over TCP or back then over a reliable transport. That was not TCP. Before SMB2 multi-channel, you had a completely one-to-one correspondence between something like a connection between one client and one server and one TCP connection. Yes, I know there were these Citrix these Citrix terminal server cases where you could open multiple TCP connections and to a single server, and you had register switches to enable and disable this. But in general, you have one client, you have one server, you have one TCP connection. With multi-channel, they got more than one, but the essence is that we have a reliable transport. SMB2 multi-channel actually widens this, and it's, of course, for two aspects. One is performance, and the other one is if one network connection dies, you can seamlessly just use the other one, and yeah, so you have transparent failover when one network connection dies. Multi-channel opens many different problems, many problems that we didn't have with just a single TCP connection. For example, one aspect is the server wants to break a lease. It sends out the lease break over a connection, and it can't really know whether this lease break has arrived until the client has reacted. And if we are now in a multi-channel connection, in a multi-channel situation, the client might come over different connections with more requests and so on. I have sent out a lease break on connection A. Connection B is active, and it's not giving up its lease. Many things can have happened. And one thing is that the client has never received this lease break over connection A. So we have to really monitor low-level TCP stuff to figure out whether the client has received our lease break and resend this over the other connection and so on. And this applies to both client and server. And I just named the server example, trying to break a lease. It's the same for the client. You send a create request. You can't really know what happened to it until you got the reply. It might have happened that the client couldn't send. It might have happened that the network has disconnected. It might just be that the server is slow. So you need a way to properly handle modify a non-idempotent request, and SMB with multi-channel takes care of this with channel sequence number and so on. NFS comes from a different transport world. NFS historically comes from UDP, and we just learned that the NFSv4 RFCs or the NFS server implementation in the kernel tries to get rid of UDP, which is the good thing. But UDP is still, from the RFC perspective, a valid protocol. And up to NFSv4.1, and this is the way I read the RFC, up to NFSv4.1, there was no real properly defined duplicate request cache handling. It was all like many heuristics, which of course stood the test of time. So that wasn't bad, but it wasn't really, really well defined in the sense that, okay, in this case you did this and the server has a definite way to tell, okay, the client has gotten the reply to the request, I can throw away the request from my duplicate request cache and so on. And it was only NFSv4.1 that introduced proper DRC handling. And they had to introduce a session using the session as a context for when how the client could tell the server, hey, I have now received a response to request X. Please throw away request X's reply from your DRC. So, and it took really the time until NFSv4.1 that this was properly defined. Essentially, my reading of the RFC is that with NFSv4, the whole basics of the protocol completely changed under everything. And yeah, but this is not really for the interoperability piece. This is a slide that comes from my reading of the NFS RFCs. Okay, locking. Enter the world of locking. Share modes, share reservations. SMB from the beginning was a stateful protocol. And files always had to be opened before use. This is not the case for NFSv3. You just need to have a handle, a file handle, and you can do anything with it. There is no real open state in NFSv3. For single tasking DOS compatibility reasons, and this is, I think, why the share modes were initially developed. You had to protect one DOS application from other DOS applications stepping on its toes. So you have Word running, Word being on a single tasking, single user operating system. It knows it's alone on the file. And this assumption is no longer valid if you have a multitasking operating system or if you have a network system. But because and as I said, Microsoft was good at maintaining compatibility, they had to put some protection into the protocol at a very early stage. This is why they said, okay, the default open call on a file was an exclusive open, an exclusive share mode in whatever exact mode. So the unmodified Word program opened a file, nobody else could open the file, so Word still could maintain the illusion that it's alone on that file. And this is how the share modes, the per file locks, I think, were developed and still are there until today, which is a good thing. NFSv4 was completely, it was designed as completely stateless. And so all the locking that clients wanted had to be done in external protocols. Network Lock Manager, some more protocols where the client could tell the server, hey, I just rebooted and something like that. Chuck could tell me, as I said, tell me when I'm talking completely bullshit. So locking was done in external protocols. And up to today, from my reading of the NFS RFCs, it's still a problem for the server to actually detect when a client has died and vice versa. NFSv4 identifies clients and servers and adds state to the protocol. It's not really an open call as we see it in that they have as we see it in SMB, but it's something like that. All the locking state that is tied to an SMB connection, to a TCP connection in the SMB world, in the NFS world, is tied to leases. What is a lease? A lease is essentially a client tells the server, I'm still alive. A client as a machine tells the server, I'm still alive. And so the server can somehow, after the lease expiry, drop the locks that the client has been establishing. NFSv4 introduces share reservations, which is what we in the SMB world call share modes. And I read somewhere, maybe it's even in the NFSv4 RFCs, that this has been done to accommodate Windows clients. Again, somebody read the Windows specification or the Windows documentation, and the NFSv4 specification omits one central piece. From my perspective, it's the file share delete. So in the SMB world, you have in the share mode bits, you have 3 bits, which means that I can open a file in a mode that prevents others from reading, others from writing, and others from messing with the metadata of the file. Essentially, I can prevent others from deleting the file while I have it open. And these 3 bits are completely independent from each other. NFSv4, coming from a Unix file system model, has problems with this. Because when you look at it, when you want to prevent others from deleting a file while you have it open in the Unix world, essentially you have to protect the directory. Because an unlink in the Unix world just means I decrement a pointer, I decrement a counter in the inode, and I remove an entry from a directory. That's all it is. This protects a different object than the inode as such. And so this is my assumption why we don't have a file share delete bit in the share reservations of NFS. And this is something that essentially when we want a common locking infrastructure, we have to take care of. Byte range locks, they differ slightly. In particular, overlapping locks are handled differently. But I think that is something we can deal with. One interesting thing is NFS read can explicitly ask for, even though we have mandatory locks, can explicitly ask for overriding mandatory locks. So if somebody has an exclusive lock on a byte range, the NFS client can still override this. A super read, yes. Log state management, and this is, I just have 10 minutes, I will just skim over this. In SMB, all this log state management is tied to a file handle. NFS invents different namespaces, or has invented different namespaces, and I don't really know why, but I can only guess that for historic reasons, NFS doesn't really have a fixed file handle that automatically goes away when the TCP connection goes away, for example. And yeah, this is one major difference. All this, this log state management, when a client goes away, first we have to find out when the client actually goes away. There's a difference, either the TCP connection is closed in the SMB world, or the client lease has expired, or there's policies around this. Client caching. So in SMB1, we had oplocks, which is the permission to cache contents. Oplocks can, of course, be broken by conflicting opens. They cannot be reacquired in place on the same file handle. SMB2 introduces leases, essentially fixing this aspect by being able to, when you lose the permission to cache for read, for write, for whatever, by conflicting opens, you can re-establish this on an existing file handle without losing your locking state. That's one of the main things that SMB2 leases do better than SMB1. SMB2 has directory leases, and NFSv4 also has similar concepts. But we need to really look at the fine details. What is actually permitted to be cached? And we need to define the semantics. What actions on the file server, what actions on conflicting clients really trigger what caching permission to be broken on the other side of the protocols. So there's a lot of work ahead of us if we want to make this work properly to define the fine details in test cases, in test matrices, for example. So, next steps here. We want to cooperate in the world, in these two worlds. And this is now from the technical details that I described, more going into the world of whatever, real deployments. And what I see at customers, two problem areas. The first is identity mapping, and the second one is ACLs. Identity mapping, I mean, these two topics are never going to go away because they are fundamental problems. As I said, Windows identities are SIDs, 128-bit IDs that are whatever given to us by Active Directory or some other source. Unix has 32-bit identities. And even in moderately large organizations, 32-bit is just not enough. And so if you now come from an Active Directory world and you want to map something in the Unix 32-bit space, this is all sorts of complexities that you can imagine, all sorts of confusion. This remains complicated. And I don't really see a good solution once and for all for this problem. Steve looks like he has an idea, but...
I was remarking because I remember when somebody brought this question up on the Linux SIDS list, Linux shot down immediately. 32 bits was, we're not changing it.
Yeah.
And this was a few months ago, right?
Yeah. There was a proposal, I guess, that we get 128-bit UIDs in the Linux kernel just to expand the space to live in. No chance. ACLs, and this is really depressing, kind of depressing to me. Everybody has to do their own ACLs. I mean, I have done programming on top of Andrew file system. They have their own ACL model. You have POSIX, you have NFSv4, you have whatever draft POSIX ACLs in different detailed flavors on Solaris, on Linux, on whatever other proprietary Unixes. Everybody does subtle differences, has subtle differences. Then S3 comes around the corner. They started with ACLs, and they found out that ACL sucks. ACLs suck, and now they recommend POSIX. They recommend bucket policies, whatever that is in detail. I have to learn about this. Microsoft then extended ACL with conditions, and one question I think I have to answer at some point, whether you can put the bucket policies that Amazon has invented into a conditional Windows ACL just for a common representation somewhere. I mean, this is really a mess, and I've been living in this world like for 20 years. I can only hope that we can come to some conclusion somehow how we do this. Yeah, who needs to talk to each other? I mean, in the kernel we have KSMBD and KNFSD, and I had hoped with KSMBD to enter the Linux kernel that, for example, we have a chance to get a common locking infrastructure to represent share modes with a good kernel API, to get a common infrastructure for leasing that we can also in user space participate in. And I haven't really watched closely, but I haven't seen any discussion on Linux Wiki News or something that we get a good lease API, for example. This in the kernel, it might happen at some point. In user space, we have, in the free software world, we have Ganesha, we have Samba. I can only imagine that proprietary storage vendors have their own problems there. They have their SMB, they have their NFS. They need to talk, and I can only hope that if there is a proprietary vendor, you have test cases, you have a definition of NFS and SMB cross-protocol semantics at least, that you share this. I can only hope for this. And then we have people who, or we need people, or we have to do this. We need to document what we think is the right way that at least SMB and NFS are supposed to work together. And put this into test cases that are freely available. And this kind of concludes my talk. And tomorrow at 7, and tomorrow at 8, there is, in one of these rooms, Cyprus, there's a BOF about pretty much this topic. And how can we live together? Thanks for your attention. Any questions left? I mean, I had a few questions.
I'll talk tomorrow.
Okay. Then I think downstairs there's a reception, there's some food in front of the Plugfest room. Steve?
So one optimistic thing to close on, remember Jeff Layton?
Yes?
So as he was dealing with SMB stuff, and as he was dealing with POSIX stuff, and NFS stuff, he came up with a better POSIX locking model for Linux.
Yeah?
Remember? So, POSIX locking, we know, are broken by design. But having developers who work on both, like Jeff Layton, they did actually get something in Linux that kind of built.
Yeah.
So I guess what I'm saying is don't be hopeless about it, because we did see progress that, for example, in the byte range locking world, that was years ago, but there's still hope.
Yeah, but the comment was that there was one developer having lived in both worlds, and he found some aspect one tiny aspect that he could improve upon, and he did so. Open file descriptor logs, OFD logs. And yeah, but this comes back to one of my first slides. These protocols are too big for one developer to live in both worlds really completely. And that's one of the problems I see. Okay. See you tomorrow at 8.